Okay. Hey everyone. This is a weird setup, but whatever works, right? So I want to demonstrate a few more vector problems so that we can kind of understand a little bit what's happening here. So the first thing is that I kind of want to emphasize this notion of direction and the impact that has on movement and the forces in general, right? So, kind of the idea of if you're pulling on something, but you're kind of at an angle, then the amount of force that actually applies to that direction that you're wanting it to move is not going to be as strong as the force in general, right? The idea is if you're trying to scoot a chair along the ground, you want to push on it the direction you want it to go, not kind of like at a weird angle pushing something into the floor at the same time as just this way, you're going to be losing some of your energy, which I hope the example that I'm about to do makes it a bit more clear what I'm trying to say about that. So let's consider this example, right? So let's say that we have something like a fan boat. Um, and let's say that the fan wasn't installed at the right angle. So instead of installing the fan in such a way that all the force is just pushing you along, let's say that somehow the fan is kind of turned a bit. So really crazy picture here, but let's say that, let me represent this in blue. Let's say that we're at an incline of 30 degrees. And I'm trying to figure out a good place to put that in this picture. Um, let's say this is inclined 30 degrees. And normally, let's say that this is able to move or pushes with a force of 500 pounds. So if I'm calling this vector F, it's inclined 30 degrees and pushes with 500 pounds of force in the direction that it's going. Well, how do we find the vector that represents the force that the fan is pushing in? Well, then we would have the classic cosine 30 degrees, comma sine 30 degrees. And that is just representing the direction, but then we need to represent the magnitude by multiplying, by scaling that vector by 500. So again, this is the vector F representing the fan. So when I do cosine of 30 degrees, that gives me my root 3 over 2. Sine of 30 gives me 1/2. So then this vector is 500 times root 3 over 2, comma 1/2. Yeah. And this turns out to be 500, or sorry, 500 divided by 2 gives me 250. So this is 250 times root 3, comma 250. This represents the force in both directions. So how can I figure out the force that is applied just purely horizontally speaking in this situation? Well, because the fan is aimed up a little bit, we're losing some of the energy here, right? Some of the pounds of force that is pushing the boat along is pushing it upwards, and we're kind of losing that, right? So let's say, and we're kind of ignoring a little bit of like what that means for buoyancy and it bobbing up and down in the water, right? We're not thinking of it that deep, just very literal with what I'm telling you. Don't think any deeper. Right? The classic physics situation of ignoring air resistance, blah, blah, blah. So, looking at this, this is the vector that represents the fan and the force there. So now let's figure out uh, how much movement it's giving us just horizontally here. Well, this means that if we do the projection of this vector, F, we want to project it onto that which is purely horizontal. But remember the thing that I did in class today, as I said, the projection of a vector v in the direction of u, if we normalize u, that is, make it find the vector that goes the same direction as u but is only 1 unit long, a unit vector going the same direction as u, then the projection of v onto u is going to give us the force that is applied in the direction of u. So what is the direction here? Can we get a vector that is 1 unit long going in the direction of just this purely horizontal line? Well, sure, we want to go 1 unit to the right. That's just 1 comma 0. So we want to project my force onto that unit vector going that direction. Well, this means that from the formula, we would do u dot v if it's projection of v onto u. So in our case, 250 times root 3, comma 250 dot 10 divided by the norm squared, or sorry, the magnitude squared, times the vector that we're projecting onto. Well, the dot product of these two vectors, 250 root 3 times 1 is 250 root 3, and then 250 times 0 is 0. So that's just plus 0 on top. Now the magnitude of that vector, again, by this setup, is meant to have unit. Oh, hello. My video is frozen. Uh, okay. Okay. Is meant to have magnitude 1, right? We're projecting onto this vector that is supposed to be of length 1. What is the length of that? 1. So 1 squared, and then we're multiplying this scalar by this vector. Well, 1 squared is 1, and dividing by 1 doesn't do anything. So really, this is 250 times the square root of 3, and then we scale the vector 1 comma 0 by that. So this just gives me the vector 250 root 3 comma 0. So this is the force vector for how the fan is pushing us that direction. So how much force is the fan applying in the direction of this vector? If we were clever, we wouldn't need to do this projection thing in this really specific scenario because the vector 1, 0 is truly just saying, hey, going to the right, right? This question is just how much is this vector pushing us horizontally? Well, we should be able to just read that off. That is the horizontal component of this vector, 250 times root 3, right? So represent the force purely going horizontally. That's just the vector that represents only moving horizontally, that same amount. So this question didn't truly need the projection version, but I'm kind of demonstrating how we use the projection to accomplish that. Okay, so let's say instead of wanting to know the force applied purely horizontally, what if I wanted to know how much of this force is applied to a vector that's going kind of that direction, but not totally. So what if the incline was just 15 degrees? So let's write this problem out. Um, find the vector representing the force done in the direction at 15 degrees by the vector from the problem 250 root 3, comma 0. Oh, no, comma 250. So what is this saying? We have our boat and our fan is turned upwards. In the water. And there is this force caused by the fan that's pulling us forward. But then there is this magical new vector that this problem is introducing that's just the direction given by aiming upwards 15 degrees. So instead of going the full 30 that the fan is aimed, we're just asking how much force is this causing in that direction? So this is a different problem than before because with the previous example, we just wanted the horizontal component. But now this is some magical new vector that's saying, okay, well, how much is it causing in this direction? So we, this is forcing us to use this projection notion. We're just projecting this vector onto the blue one. Or sorry, we're projecting the blue one onto the green one. Well, for these issues, we want a vector with magnitude 1. We want a vector of length 1. So in order to get this green vector with length 1, we genuinely just need to do cosine of 15 degrees, comma sine of 15 degrees. So now we are going to project f onto this vector. So I'm going to call this vector A just to give it some name. And so in order to find the vector representing the force done in the direction of 15 degrees by the vector that we got from the first problem that we called f, then this answer, is this the projection of f in the direction A, projection of f onto A, right? Because automatically this setup, cosine of angle, comma sine of that same angle is on the unit circle, so that vector with those same components has length 1. This is 1 unit from the origin. Okay, so now this is genuinely just a matter of following this formula, doing the dot product, and so on. I don't have the calculator here, and if I were to pull my calculator up, it would derail things a whole lot. But the important thing here is setting this up. Now I'm just asking you to find the projection here. Okay, so in that sense, there's not nuance. These problems are very straightforward. With the ambiguous case of the law of sines and solving for the angles and law of cosines, there's some, oh, well, let's do this angle first, or decision about like, okay, well, which side am I going to solve for? Which right? There feels like a little bit of uncertainty in terms of how you exactly approach the problem. But these vector physics applications are not open in such a way that we're really going to be tackling, oh, which approach do I want to use? These are kind of straightforward. Now, again, you can do some different approaches. You can use different versions of the work formula that we talked about today in class, but those aren't so vastly different that you're truly kind of approaching this in a fundamentally different way. There's less free will with these problems, which is in a sense helpful because there's only one way to go. So okay. Now again, there's this new concept of work that is absolutely worth talking about. Okay. So work is just this idea of how much did it take, or yeah, how much effort did it take when this force has occurred over this distance, right? So let's say that we have a car moving with, let's say, 200 pounds of force along the highway, and we're going to go, let's say, not two again, 320 feet. Then there's a question of how much work went into that. How much work does it take to move 200 pounds, 320 feet? Right. So it's this question. It froze again. There's this question of how much effort does it take, right? How much gas do I need to move my car that forward? Uh, right. So that is where work is relevant. Um, Now, this one is very kind of straightforward because this vector only has a vertical component, or sorry, horizontal component. You're only moving a horizontal distance. So it is just a matter of multiply pounds by distance, right? This would just be 200 times 3,200. Um, right. But the question becomes kind of nuanced when it's something like, oh, I have my force vector happening in a different direction than where I'm trying to move. So let's say, what do we want to do? We have some slope, some constant slope, and we have a block of ice, and it's sliding down the slope. Now, to get from the top to the end, let's say it's 50 feet horizontally, and our block of ice weighs 20 pounds. Then we can ask this question of how much work went into moving this ice 50 feet over, right? Because now the things are not always happening in the same direction. Okay, so let's start this problem. So we need to acknowledge, I guess, for one, that work is applied in the direction that the object is moving. So it's not like we get to say that the work is kind of done just purely horizontally speaking, right? Because this thing is moving down the slope. So we kind of have this issue of the work is done along this vector. So let's call this vector that is the slope S to represent that hill, or I guess I could call it H to represent that hill, huh? And then we have this downward force of 20 pounds as well. Now, so we have three formulas when we bring up the idea of work. We have the magnitude of this projection vector times the magnitude of the direction, the distance that we move, the dot product of the force with the direction, and then this cosine theta times the two magnitudes. Well, I, for one, sometimes see this theta and get confused over which theta is supposed to happen here. Do I want it to be the 60 degrees, or do I want it to be the other angle that happens up here that's 30 degrees? So maybe I'm unsure what theta is supposed to be. So for that reason, I'm going to kind of ignore this formula. So now I can find the projection and I can find the dot product once I know what my two vectors, my force and my direction vector are. Now, this problem is a little bit special because I didn't tell us, we don't know immediately, right, what this vector H exactly is. But I know its horizontal component is 50. So what's left to find out is the vertical component. But I know the vertical component has to correspond to this angle of 60. Essentially, I'm saying we need to make a right triangle and figure out what this missing side, what the opposite side is to this angle. Well, SOHCAHTOA says that sine of 60 should be opposite, which is this vertical part that I'm trying to find, over the hypotenuse. So we don't want to use sine, right? Because we don't know the distance of the hypotenuse yet. We could figure it out, but that's kind of what we're heading towards, right? So I know the adjacent side and I want to know the opposite side. So which SOHCAHTOA do we want to use? Tangent of 60 is opposite over adjacent. So the missing side that I'm calling the vertical component over the adjacent 50. But I know that tangent of 60, I don't know what tangent of 60 is, sine of 60 over cosine of 60. And sine of 60 is root 3 over 2, and then cosine of 60 is 1/2. So root 3 over 2 divided by 1/2 turns into just the square root of 3. That's what I wanted to guess, but I didn't want to guess. So, okay. The square root of 3. So this means that V over 50 is tangent of 60 degrees, which is the square root of 3. So to solve for V, I multiply both sides by 50 and get that V is 50 times the square root of 3. Okay, so how can I represent the vector H? The horizontal component is 50 and the vertical component is, sorry, 50 times the square root of 3. So now that is this D here, right? The direction that we're trying to move is represented by this vector. And now F is this remaining piece to find. Well, how do we represent the force here? What direction is force happening in? Well, F, our force right here, is just the weight that's pulling down on the ice cube. Well, that weight is just going to be 20, right, vertically. That's pulling us downwards. So I'd say The easiest formula here is going to be the dot product because we have the zero here with F, right? So we can do F dot H is going to be 50 times zero, right? Multiply the X values together, and then 50 root 3 times 20, which is 0 plus, and then 20 times 50 is 1,000. 2 times 5 is 10, and then we have two extra zeros. So, yep, 1,000 root 3s. So the work that has been done is, why, where'd the other zero go? 1,000 times the square root of 3 is that number that we get in the end. Okay, so again, whenever we're talking about work, we have these three different formulas that come up. Now, any of them do work, no pun intended. We can find the projection. That's relatively easy. We can find the dot product. That is pretty easy, I would say. But it is a little bit of a challenge knowing sometime like which we're doing. Um, so yeah. Anyway, okay. Very good. That's kind of the review that I wanted to get at. Um, I don't have a good outro. Sorry, there weren't any Subway Surfers for this video. That's all I got. Bye bye.